in our Module 2, 8.2, Measure of Running Time. In this part, we will do some, very abstract discussion. We want to look at how do we do the analysis of algorithms. First, let's look at this question. What is the analysis of algorithms? We did a little bit before. So we saw how did we use counting technique to get a number of comparisons, the number of multiplications, the number of operations to measure the performance of algorithms. For this video, so we want to look at the theoretical background behind that idea. All right. So usually after we get a solution, so we need to do some analysis. So we want to know, is this solution good enough? Is there any room we can improve it? Right? Is this solution optimal? So all those things we discussed in our Module 1. So now let's look at the resource we used in an algorithm. When we talk about the resources used in an algorithm, usually we look at these two types of resources. The first type, the primary resource. So that is the running time. So the most important factor we want to look at when we do analysis of algorithms. The second one, less important, but also we should consider, especially for some special situations. That is the memory space we used in our algorithms. The reason, it is secondary, so not as important as the execution time, the running time. Because first, usually, the modern computers, memory expense becomes cheaper and cheaper. So people can afford larger capacity memory space. But even that, it is still, memory consumption still an important factor for our algorithms' overall performance. The reason is it may affect the running time. So if you do not use your memory space efficiently, you can quickly run out of your memory space and eventually make your algorithms running slower and slower. Finally, nobody can use it. So for that reason, we want to try our best to reduce the memory space used in our algorithms. All right. Methods used to study analysis. Basically, two methods. So for this class, we will use both two methods to study our algorithms. The first one, theoretical method, and the second one, empirical method. For the theoretical method, we will do a lot of mathematical operations, calculations. So we need to apply all the methods we learned in math. So the calculus, discrete math, mainly we use methods from those two classes. Calculus, 1800 calculus, discrete math, Math 3000, yeah, we mainly use those two classes. The knowledge in those two classes. Then, to do this theoretical analysis. For empirical side, we need to do our programming projects. So in our programming projects, we will write our programs to implement certain algorithms, and we want to check the performance, efficiencies, compare, which way we get better performance. Yeah. That's the empirical analysis. Yeah. All right. Next, let's look at efficiency of algorithms. The first concept, time efficiency. So regarding the running time, how efficient it is. Another terminology we also use frequently, time complexity. Yeah. Then space efficiency or space complexity. Yeah, the secondary resource. We also need to do some analysis on it. Yeah. All right. But here we like to discuss a little more deeper for the space efficiency. So how do we do it? So we consider extra space used. So what's the extra space used? The space used for input and output, that's the normal use, right? You have to use certain storage spaces for input output. But other than that part, many times we need to use extra storage space. So in addition to the standard space we need to use some extra space. So that part, we need to do analysis. We want to reduce that part, that consumption. Yeah. So for that consideration, we define a new concept. It's called Inplace Algorithm. Inplace Algorithm. Yeah. Here in our previous video, we learned that in-place concept, but this one different. That one in place, that's the real element in its right place. That's the meaning, straightforward meaning. But here, this in place related to space efficiency. Okay? In-place algorithm. Yeah. What's the meaning of that? The extra amount of space, we only look at the extra part, excluding input-output storage space. Yeah. That amount is bounded by a constant number. A constant, right? It could be 5, could be 10, could be 100. Yeah. But as soon as you determine that amount of space used for your algorithm, then it is fixed number. Fixed number, that means even you increase your array size, you use your algorithm to process more elements, but the extra space you used always this much. You never need to increase this extra space part. If your algorithm has that property, we call it is an in-place algorithm. So you can see, if you can get an in-place algorithm, that is always a good choice. We like to use that in-place algorithm. Yeah. All right, next concept, input size. So I want to talk about the input size. Yeah, when we talk about data size, yeah, there are two different meanings. The first one, we are already familiar with that meaning. Yeah, we use it several times. That is the number of data items in your input, the array size. So when we use array to store our input data, the input size is the number of elements in the array. So that meaning, so we're familiar with that. But the second one, there is another meaning. So we haven't seen that kind of questions, but let's look at the meaning of the second type. The magnitude of number. The value, the magnitude. Capacity, we do not call capacity. The larger, small, right? The larger, small. How large? That one sometimes could be interpreted as the size, depends on your questions. So let's look at the question. So this time only one number, the capacity. The value number, big or small, only one number. One number means the size. How to see that? Let me give you a simple example. This example. Checking primality of a positive integer. Prime. You know prime number, right? If a number is prime or not. 2, 3, 5, 7, 11, 13. So those numbers, they can only divide it by 1 and themselves. No other factors other than 1 and themselves. Those are the prime numbers. All right. Now we are given a huge number. How do you determine if that number is a prime or not? Usually, that problem is very hard to solve. If a given big number, if it is a prime or not, extremely hard to solve, even using the modern computer, still very, very hard to solve. In that case, you only give one number, one big number. So the size is the magnitude of that number, the value of that number. That's the size. If the number grows many, many times larger, then the problem size also becomes larger. So that situation, that corresponds to the magnitude case. All right, next. Measure running time. So this time we want to find a good measure for running time. So what is the good way? So we want to have some scientific method, reliable method, good, solid method to do it. First, the measure should be stable regarding the running time. Running time directly. So if we really clock the actual execution time, that's not very stable, because many factors can change that execution time. Many factors. Here I do not list those. You can imagine. We need a stable one. So it does not change easily. Very stable. So when you change certain things, if that's not a really critical, then it should be the same. All right. So that measure should not rely on the hardware, computers. Someone uses a very fast computer and someone uses a very slow computer. We don't want to use the direct execution time to compare the efficiency of algorithms, because they're the same algorithms. In a supercomputer, it runs very fast. In a very old computer, it runs very slow. But the same algorithm we should use the same measure, not related to computer hardware. Yeah. So that's one. Another, it does not rely on the quality of the program. Even the same algorithm. Yeah. When you write a code, some programmers do not have a lot of experience, so they do not know how to make faster programs. So they handle things not very efficient. So they waste a lot of resources. But for some other really experienced programmers, they know how to save resources. They know how to use optimal ways to do the operations. So they can implement the same algorithm very fast. So we do not want to factor in that kind of difference. Yeah. So now you know how stable our measurement should be. Yeah. All right. The main approach we use. Yeah. We use the basic operations. That's stable. That does not rely on hardware, program quality. Yeah. What's the basic operations? Yeah. The operation contributing the most to the total running time. Yeah. Because when you look at the total running time, okay, because you have several operations, some operations contribute relatively small, and some operations contribute a lot. So we look at the most contributed operations. Yeah. All right. Then we count the number of operations used in the algorithms. When we do that, we can get stable measure. Not related to hardware, not related to the program quality. Yeah. All right. Next, how do we connect basic operations to running times? Yeah. Yeah. First, we need to identify basic operation in the algorithm. Yeah. Because usually there are several operations. Some of them may not be basic operations. Some of them are. Yeah. So usually, the most time-consuming operation in the innermost loop. Yeah. When you implement your algorithm, you need to write for loops, while loops, infinite loops. Okay. Yeah. The loops. Yeah. Yeah, not infinite loops. Yeah, loop and nested loops. Yeah. So many times your loop could be nested, multiple levels. Yeah. Then look at the innermost. Which operation you do in the innermost loop? Because that operation will make impact in all the levels from innermost to outermost. Okay? Innermost to outermost. Okay? Yeah. Then that operation will make the most contribution to your algorithm running time. Yeah. So for that one, we will choose as the basic operations. Yeah. Some examples, yeah, for the problems we have learned at this point, yeah, we can see that easily. The problem one, evaluate a polynomial. Multiplication is the basic operation. Yeah. For problem 2 and problem 3, find the minimum and sort an array. Comparison is the basic operation. Okay? Yeah. So you can see in that case, you just count the number of those operations. For example, for problem 1, you do not need to count the number of additions because it is not basic operation. Yeah. It's a minor term, so we can ignore. Yeah. So that's the concept for this video. Yeah. In my next video, I want to discuss the real analysis part, the theoretical analysis part for our running time efficiency based on counting the basic operations. All right. Yeah.